Okay, we're going to start chapter 15 today, and chapter 15 is about equilibrium. Whenever you have a chemical reaction, you start with your reactants and you end with your products. But a lot of reactions don't just go one way, like the reactants producing products. Sometimes some of the products go back and become reactants. They break down or change their bonds or whatever. So when you get to the point where the amount of reactant and the amount of product aren't changing, not the same, but when they're not changing anymore, the equation is in what they call equilibrium. And when we're talking about equilibrium, we're dealing with two things. We're looking for things that are in the gas phase, and we're looking for aqueous. If we're talking about solids and liquids, they don't count. And again, I'll show you more of this later. Okay, so here's the concept of equilibrium. Here we have N2O4, and we're reacting and we're making NO2. Okay, the equilibrium occurs when the reaction and its reverse reaction proceed at the same rate. Okay, so I'm producing these, but as I'm producing these, some of them go back. Okay, so the reaction goes back and forth. Okay, when it gets to the point where this amount and this amount aren't changing. Now they don't have to be the same. The amounts, like if this is 2 moles and this has to be 2 moles, not necessarily. But you're going to do an activity when I'm done with this lecture, and hopefully that'll explain it more. But anyway, by this, and they've done this reaction enough, they go by the color. When the color stays the same, then they know that it's in equilibrium. Okay, here's another, this is a good graph. Okay, so this is our reactant, and as you produce product, of course, it goes down, the amount goes down. And then here's our product. It starts at 0 because the reaction hasn't started. But through time, you know, you're producing it, but some of it goes back. Now it reaches equilibrium, you'll notice right here. See how NO2 isn't changing anymore and N2O4 isn't changing anymore. When these numbers are staying the same, so the amount of this that's going into producing product and the amount of product that's going back into reactant, when they're the same, not here. Right here, what this means is, yes, the amounts are the same, but they're going to change, you know, through time. So it's not when the amounts are the same, but it's when they don't change anymore. This is equilibrium at this time because this number isn't changing anymore and this number. They do not have to be the same. Now, on this one, they are the same. Okay? That just happened to be, you know, the amounts were the same, but that doesn't happen for very many reactants. They're more like this. The reactants is, you know, the number is actually getting lower, the concentration, because you're producing product, and the concentration of product is increasing. But when the two of them don't change anymore, then you're at equilibrium. Okay, so as it approaches equilibrium, both the forward and the reverse reactions are occurring and at the same rate. Okay, so equilibrium was in the forward and reverse reaction are producing at the same rate. Again, this is the most common. You will see once in a while where they're the same amount, but not very often. It's more like this. And again, it's not when they're equal, when the amounts are equal, but it's when the amounts aren't changing. Okay, when they stay the same, even though the reaction's still going on. Okay, once equilibrium is achieved, the amount of each reactant and product remains constant. If you want to change that, you have to do something like change the temperature, add some more reactant, add some more product, do something. But once equilibrium, once it's got to this point, if you kept measuring this, it would still just go straight across both of them. Okay, so if you don't do anything to this equilibrium, you don't do anything to change it, like again, change temperature, change volume, change pressure, something like that, then it's going to stay the same, no matter how long you run the reaction. Okay, a system, it's in dynamic equilibrium. Again, the products are being made, but the reactants are also being made at the same rate. In other words, the product is reversing back to reactant, and the reactant is making product. When they happen at the same rate, then you have equilibrium. Okay, it does not change. As long as you don't change any of the factors involved, like I said, then that number won't change. It'll stay the same. Okay, and it has to be a closed system, because if you have a system where you can, you know, if your product is some gas that escapes into the air, obviously that's going to change your results. So the reactant or product cannot escape the system. It has to be a closed system, and then that will happen. Once they reach equilibrium, you can run that reaction for days and it'll still stay the same. Then once they reach equilibrium, it will not change. Okay, so there's a ratio of concentration in terms of a constant. There's something called K sub C, and it's the equilibrium constant. Personally, I wish it was K sub EQ, equilibrium, but they call it K sub C. Remember K we talked about last chapter was the reaction constant? Now we're doing the K sub C, which is the equilibrium constant. And if you want to write K sub EQ, go for it. I don't know why they don't. I don't make up this stuff, you guys. I just, go through and follow the rules. Okay, so for writing an equation for an equilibrium reaction, since in a system an equilibrium goes both forward and backwards. Now most of the time when we write equations, we just write an arrow going one way because the reactants produce the product, reaction's over. But in an equilibrium reaction, what happens again is you're producing product, but some of the product is breaking back down into the reactants. So we draw an arrow like this. It means it's going forward and backward, forward and reverse. Okay? Here's one I was just showing you. With N2O4 is a gas producing NO2, which is a gas. Okay, so I'm taking this and it's breaking down and it's producing this, but these guys are also combining to make this. So it's going back and forth. That's a reaction that can go forward or reverse. Not all reactions can do this. Okay. Okay, so if we're talking about equilibrium, okay, the rate forward equals the rate in reverse. When you get to the point where the rates are the same, the amount of product being produced is the same as the amount of reactant being produced, then you're in equilibrium. If you're doing it from this reaction back here, okay, you always have the product on top and the reactant on the bottom. So here we go. And again, this had a coefficient of 2, so that's why that goes there. So the constant forward and the reaction rate basically forward is the same as the reaction rate in reverse. Okay, here's the concentration. This is of our product and this is of our reactants. And again, forward, producing product, reverse, and it's a constant. Okay, and so when those two equal each other, we're at equilibrium. Okay, so again, here it is, the constant forward versus the constant in reverse. And again, I'm going to show you how to determine those constants. Okay, it's similar to what we did last chapter with the rate constants. We got to figure those out, but every reaction is going to be a little different. Okay, so rewriting this, it becomes, here's our KEQ, yay, right? You put the product on top, and again, if there's a number in front, if you used a coefficient to balance it, it's to that power. It's kind of like when we did our reaction rates. Okay, and then again, this is our reactants on the bottom. So forward and reverse, that's what the F and R. At first it was like reactants. Oh, why isn't that products? But it's forward and reverse. Okay. So one of the most common equilibrium processes, it's one of the, probably the biggest as far as industry, if you're talking farming, is the Haber process. And the Haber process is when we make ammonia. Okay. In the springtime, you know how you get stuck behind those anhydrous ammonia tanks that people are pulling to put in their field? This is how they're made. Okay, they take nitrogen gas and hydrogen gas, the two combine to make ammonia, NH3. And this is super, super important in fertilizers, in all kinds of industry, in farming, which is in North Dakota kind of important, right? Okay, so the equilibrium constant, okay, would depend on, this guy would go on top, so we'd take the concentration of NH3 to the second power over the concentration of H2 to the third power and the concentration of N2 just to the first power. Okay, so again, the products go on top, and then whatever their coefficient here, we've got hydrogen, and there's a 3 here, so it's to the third power and N2. Okay, that's how we would figure its reaction constant. And again, that's similar to what we did last chapter. But now for an equilibrium, what happens is we have to figure it out according to how they change. Okay, so here's another one. We've got nitrogen monoxide and chlorine gas, and then we get, I have no idea, NOCl. Okay, so again, we put this guy on top with a 2, and then we put our chlorine and 2 of our, so when we fill in our concentrations, we can get our numbers. Okay, here's another one. Okay, this one I'd fill 2, I'd have the concentration of carbon monoxide to the second power over, see now this is a solid. Solids and liquids, if they're in there, you don't include them in equilibrium. The reason why we have equilibrium is because the gas particles are moving around. Okay, or aqueous. If it's an AQ, we count those two because then we have particles moving around. But with a solid and a liquid, the particles don't move around to affect equilibrium, so we don't count them. So we don't have to worry about this guy. We just have to worry about this guy. So our equilibrium, if we're trying to find K sub C, our equilibrium constant, it would be CO, the concentration of CO to the second, over the concentration of CO2, carbon dioxide, to the first. We would not use the carbon. Okay? So if it's a solid or liquid, which is kind of a pain when you're typing these out, because I usually don't put in what phase they're in, but you have to, because you have to know what phase they're in, because if they're in a solid or liquid, you don't use them. Okay? So again, if a reactant or product is solid or liquid, you don't include them in the calculation. So now I got to type them in. Okay? Okay, so what do you start with to reach equilibrium? Okay, here's the Haber process. Okay, we got hydrogen, nitrogen, and ammonia. Okay, if we're starting with the reactants, of course here's our hydrogen, here's our nitrogen, and here's our product, ammonia. Okay, when the numbers don't change anymore, okay, they're never going to be equal to each other, okay, because of the different stoichiometry amounts. So here is where they don't change anymore though. Okay, so this is equilibrium when we start with reactants. What if we start with the products? What if we start with NH3? Okay, and these guys are going to be at 0. So we're going the reverse. So this is when we start with the reactants. This is when we start with the products. And again, because it goes both ways, we're going to here's our equilibrium here. And you notice it's pretty much the same. Because these are going to be, when these two equal each other, when the amounts, and again, it's not, I don't want H2, N2, and NH3 to be the same amount. I want them so they're at the point where they're not changing anymore. That's when they're at equilibrium. Okay, some people think equilibrium, oh, that means if you have 20 grams of this, you have 20 grams of that. That's not true. It might be 20 and 5. It just depends on when the numbers don't change anymore. Then you're in equilibrium. Okay, so the figure shows that it doesn't matter where you start, whether you start with reactants or product, an equilibrium will be reached. And if you look at them, the equilibrium reaches at the same time. So the only way I'm going to change where equilibrium is reached, their K sub C, is if I do things like add more reactant, add more product, change the pressure, change the volume, change the temperature, things like that. And we'll talk about those later. Those are part of equilibrium they call Le Chandlier's principle, and I'll show you that as well. Okay, so there is our, forward and backwards, you can see, and this is where equilibrium is reached. Okay, relative amount of change is based on stoichiometry. That's why if there's a 3 in front of this, you have to use it in your problem. You have to put a 3, it's to the third power. So you can't forget about those coefficients. Okay, so I think we're going to quit here. Yeah, because the next part I'm going to show you how to actually determine it. So what I have next for you to do is a little activity where you practice reaching equilibrium with little parts. You can use pennies, you can use M&Ms, you can use Skittles. They just have to be the same. And again, you'll see in the activity, it's to show you how you reach equilibrium using differences in your reactants and your products. So that's the next thing I have for you to do. And then I'll show you how to actually figure out the K sub C. We're going to use something called Rice tables. All right. And I know it sounds crazy, but they work really well. So I'll show you those next time. So right now we're done with the first part of chapter 15.